Welcome to Pre-Calculus, Combination of Functions. This is for Math 1508 at UTEP, but pretty much any pre-calculus course would have this. Chapter 1, Functions and Their Graphs, comes from Larson's 10th edition of Pre-Calculus. Section 1.8, Combinations of Functions. So, some basic operations. From when we first learned math, we started counting, and then our teachers told us, hey, we could do stuff with this. And what do? We add, and we subtract, and we multiply, and we divide. And then we get these fractions. What do we do with them? We add them, we subtract them, we multiply, divide. We get decimals. We add them, we subtract them, we multiply them, divide them. We get irrational numbers, and we add them, and we subtract them, and we multiply them, and we divide them. And it should be no surprise that if we have two functions with overlapping domains, then we can add them, we can subtract them, we can multiply them, and yes, we could divide two functions as well, as long as our denominator is not 0. So, of no surprise, and it works out really well. When I'm adding f plus g and evaluating at x, that's f of x plus g of x. Similarly, subtraction, multiplication, they all work how we would expect them to work if we had to come up with a definition. So let's take a look at some examples. So we're going to find the sum, difference, product, and quotient, given f of x equals 3x plus 1, and g of x equals the square root of 1 minus x. I love these. These are kind of easy, so I'm going to give you a second example on the next slide that's a little more challenging, but the sum, f plus g evaluated at x, total mathematical notation here, is just f of x plus g of x. So I'm going to write down f of x, 3x plus 1, then I'm going to write down a plus sign, then I'm going to write down g of x, the square root of 1 minus x, and I am finished. The difference, f minus g evaluated at x, is f of x, and then a minus sign, and then a g of x. So I'm going to write down my f of x, 3x plus 1, a minus sign. And since my g of x is a nice little square root of 1 minus x, I don't have to worry about distributing the negative, but that could come up in other examples. The product, f times g of x, is f of x times g of x. It's important to use parentheses here because I want all of f of x to be multiplied by g of x. G of x is kind of an understood parenthesis because of the radicals around all of 1 minus x. But 3x plus 1, it's not an understood kind of package deal. So you have to put parentheses around it to say the whole thing is multiplied by the radical. In the quotient, f divided by g evaluated at x. Let's put in that missing notation here. Yes, professors make mistakes too. I know, shocking, we're human. F divided by g at x is equal to f of x over g of x, which is 3x plus 1 over the square root of 1 minus x. Now it is important in this case to label a domain. X has to be less than 1. If x is equal to 1, we'll have a 0 denominator. So we restrict the domain of our radical function even more than it would have been in general. The second example, now let's take a look at a couple of polynomials. F of x is x squared minus 2x, and g of x is negative x plus 3. When it comes to the sum, there's really no difference. I might put the second function, the g of x, in parentheses just to make it look nice. But really I'm combining my like terms, negative 2x and a negative x, to give me a negative 3x in the middle. I have my x squared, I have my plus 3, everything's cool. When we have the difference, that's when we really need the parentheses in the second function. Anything that follows a subtraction, make sure you tell yourself, really, the entire function has to be subtracted. So this negative to the negative x makes a positive, right? Positive x and a negative 3. So x squared minus 2x plus x, that's where I get the minus x, negative 3 at the end. So make sure you distribute it. Not totally necessary here with addition, absolutely necessary with subtraction. It's a good idea to get in the habit of always doing it. That way you don't have to remember, oh, do I do it here or not? The product, again, all of f, x squared minus 2x, in parentheses, has to be multiplied by all of g. And that's all of negative x plus 3 in parentheses. Without the parentheses, you're really not doing multiplication. So put them in there, make sure you can see what's going on, and then we're going to FOIL. First, x squared times x is x squared times a negative x is a negative x cubed. Negative 2x times 3 is negative 6x. Wow. Hold that thought. Alright, let's get back to this. I'm paying attention now. X squared times negative x is a negative x cubed. X squared times 3 is 3x squared. Negative 2x times a negative x is a positive 2x squared. So I had 3x squared and positive 2x squared gives me 5x squared. I thought I made a mistake there for a minute. And the negative 2x times 3 makes a negative 6x. So I combined my like terms as I did my FOIL. The quotient is my favorite because I write the numerator divided by the denominator, and I specify my domain x can't be 3, and it's all good to go. Add, subtract, multiply, and divide. We could do it with all the numbers we've had over the years, and now we could do it with functions as well. But for functions, there's a fifth operation, and this fifth operation is probably the most important when it comes to calculus, and this is a pre-calculus class. So the composition of the function f with the function g is written with this little open circle notation. Sometimes you could be lazy, call it fog. F composed with g evaluated x, and that is just f evaluated at g of x. So I'm evaluating one function using another one. The domain of the composition is the set of all x in the domain of g, right, such that g of x lands in the domain of f. In general, f composed with g of x, which I will always rewrite as f evaluated at g of x, I'll refer to g of x as the inside function, whereas f of x is the outside function. So let's find the compositions in both orders. You know, when we add two things, it doesn't matter the order we add in, the commutative property holds. When we multiply two things, unless they're matrices, it doesn't matter which order we multiply in because of the commutative property. But subtraction and division, order matters. So composition, we need to find out, does order matter? Let's see. If f of x is the cube root of x minus 5, and g of x is x cubed plus 1, and I want to find f composed with g of x, that's f evaluated at g of x, always my first step, rewriting it here. Same number of parentheses, same direction, we just kind of slide this one over and slide this big one to the end. So g of x, what is g of x? G of x is x cubed plus 1. So I replace g of x with x cubed plus 1. And then I write down the structure of f. F is the cube root of something, so I put in my parentheses, minus 5. Here it's an x. But in this representation, our composition, instead of an x minus 5, we're going to have x cubed plus 1 minus 5. And we can simplify that. The cube root of x cubed minus 4, this cannot be simplified. Think about your order of operations. Over here, g composed with f of x is g evaluated at f of x. I know f of x is this cube root function. So the form of g is something cubed, so parentheses cubed plus 1. And then I can fill in what the something is. Up here it's an x. In our composition it's the cube root of x minus 5. And in this case the cube root being overwhelmed by the cube does simplify. X minus 5 plus 1 gives us x minus 4. These results are not the same. They're not the same. This cube root of x cubed minus 4, I can't simplify that at all. It is not the same as x minus 4. For f of x equals the absolute value of x minus 4 and g of x equals 3 minus x, when I substitute g in for x, I get 3 minus x. The form of f of x is the absolute value of something minus 4, and I'll frequently call it something even when I'm in class. X is just a variable, it varies. So I take out the x, I put in parentheses where it used to be so I still have my structure. The absolute value of parentheses minus 4. It tells me what my original function looked like and allows me to remember where to substitute my 3 minus x. 3 minus x minus 4 gives me a negative 1 minus x inside the absolute values. In the other direction, g composed with f of x is g of f of x. Replace f of x with my absolute value. The structure of g is 3 minus something. Now, I didn't use parentheses this time because parentheses with the absolute values, it gets a little confusing. But 3 minus, oh, what's my something? My something is the absolute value of x minus 4. Composing functions, great skill. But when it comes to calculus, a lot of times we're going to have to decompose functions as well. So decomposing functions means pulling it apart. We need to look for the inside, look for what looks like the outside. Our function h of x is given by 1 minus x all cubed. It looks like the inside is 1 minus x and the outside is something cubed. Go with the obvious inside parentheses, inside a radical, inside a denominator, and so on. So in this particular case, I would let g of x be 1 minus x, my inside, and my outside, f of x, be x cubed. How do I know which one is inside and which one is outside? It gives that to me here in the instructions. G of x is on the inside, f is on the outside, so f is the cube, g is the stuff on the inside, the 1 minus x. There are many, many different possibilities for these answers, but always go with the most obvious. Number 9. Sorry, not number 9. This is slide 9, though. H of x equals the square root of 9 minus x. Looks to me like the inside is 9 minus x. What did I put that inside of? Well, it's inside of a radical, so my outside is going to be the radical. Let's let g of x be 9 minus x, and f of x be, I can't just call it square root of parentheses, right? I got to go backwards on that idea, and I have to put in a variable so I can make it a function. So f of x is the square root of x. Answers will always vary for this task. It's huge skill when it comes to calculus, and some answers are better than others. For example, when h of x equals 4 over parentheses 5x plus 2 all squared, one possibility, the first one that comes to me really, is let g of x be the 5x plus 2, it's inside parentheses, and then f of x is 4 over something squared, and instead of calling it something, we'll use a variable, 4 over x squared. For calculus, this would be the best one to use. And if you want to know why, watch my calculus videos and I'll let you know. Another possibility, though, is let g be the entire denominator. Let g of x be 5x plus 2 all squared. And then f, my outside function, is 4 over something, right? Our something, 5x plus 2 all squared, 4 over something. The first one better for calculus. The second one still completely acceptable for pre-calculus. Alright, so find two functions f and g such that f composed with g of x equals h of x. At this point, you should pause, give it a shot yourself before continuing on and seeing my solutions. Pause. No, really pause. Just kidding. Moving on. Number 4, I would let g of x be x plus 2, and then f of x is 1 over something, 1 over x. For number 5, h of x equals the cube root of x squared minus 4. I would let g of x be the inside, x squared minus 4, and the outside be the cube root of something. We can't use something, we can't use parentheses, we have to put the variable in so it's a function, but that's the way I think about it. Cube root of something. Alright, so a word problem example. The number n of bacteria in refrigerated food is given by n of capital T equals 10 capital T squared minus 20 capital T plus 600, where capital T is in between 1 and 20, and it's the temperature of the food in degrees Celsius. When the food is removed from refrigeration, the temperature of the food is given by capital T at little t is 3 little t plus 2. When t is between 0 and 6 and t is time in hours. So between 0 and 6 hours, and my temperature of my food is between 1 and 20 degrees Celsius. We're going to find the composition n of capital T of little t and interpret its meaning, because we have to know what it is we're talking about. We're going to find the bacteria count after half an hour, and we're going to find how long it takes for the bacteria count to reach 1500. So finding the composition. N of capital T of little t, so I put in my function here, n of 3t plus 2. And then everywhere I see a capital T, I'm going to replace with 3t plus 2. 3t plus 2, don't forget to multiply that by itself, so we'll get 9t squared plus 6t plus 6t plus 4, and then I combine my 6t and 6t to get 12t. I distribute my 20 times the times the 3t and my minus 20 times the 2, and I leave my 600 hanging out. When I distribute, 10 times 9 is 90t squared, plus 120t, plus 40, minus 60t. And then I decided to combine these to get a positive 560. Combining yet again, 120t minus 60t is a positive 60t. I still have my 90t squared, and I have a 40 and 560. I went back to 600. What is this? This is the number of bacteria, N, based on the time it's been out of refrigeration. Rather than the number of bacteria based on temperature, now we have the number of bacteria based on the time that the meat or food has been out of refrigeration. Okay, so we have these three equations, N of capital T of little t, and the number in terms of the time. Find the bacteria count after half an hour. Bacteria count, that's N. 0.5 hours, that's a little t. So I'm going to use the formula that we just found, put in a little t value of 0.5. 0.5 squared is 0.25. 0.5 times 60 is a 30, and the 600 hangs out. A quarter of 90, well, we know that half of 90 is 45. Half of 45 again, right, because a quarter is 22.5. We don't need a calculator. Plus 30 plus 600. That is 652.5 bacteria after half an hour leaving the food out of refrigeration. Gross. And what we all want to know, find the time when the bacteria count reaches 1500. We're again going to use the new equation since it directly relates bacteria and time. And in this case, the number of bacteria is 1500, so I'm going to set 1500 equal to 90t squared plus 60t plus 600. Subtract 1500 from both sides because anytime I want to solve for a quadratic, I'm going to get it equal to 0. I'm going to try to factor maybe, but I would most likely use the quadratic formula. I don't want to use the quadratic formula with such large numbers though, so I'm going to divide every single thing in my equation by 30. 0 divided by 30 is 0, 90 divided by 30 is 3, 60 divided by 30 is 2, negative 900 divided by 30 is a negative 30. And then using the quadratic formula, always simplify the radical first, and then the fraction. Negative 2 minus the square root of 364, all divided by 6, gives me negative 3.5 hours. I will never take food out for negative 3.5 hours. That's weird. It's not real life. So, negative 2 plus the square root of 364, all divided by 6, it will be 2.846 hours. About 2.8 hours if I rounded, which is 2 hours and 48 minutes before we'll have 1500 bacteria on the food we took out. Be safe. Bad food can really hurt you. And that ends this lecture. Combination of functions. Focus on composition.